For the next, we talk about the STP. For this one, I think it's more harder. For Sundray switch now it supports STP and rapid STP and multiple STP. The last one is about the STP configuration. So let's introduce STP first. STP is based on the protocol 802.1d, a protocol used to automate the loops in a local area network. For the high availability parts, we want to make the network more stable and to add the redundancy in the network. But after we increase the number of the devices, it can also bring the risk for the loop. So when the loop generates the broadcast storm, it can cause the network unavailability. And also the MAC address table shocks can cause the MAC address entries to be destroyed. So to prevent the broadcast storm and the MAC address table shocks, here we to prevent okay to prevent the broadcast storm and the MAC address table shocks, here we use the STP feature. So let's see some characteristic of the STP ports. The first, the root bridge. The root bridge is a bridge with the smallest bridge ID. The smallest bridge ID is selected by the interactively configuring PPDU protocol packets. For the root bridge, each network only has one root bridge. And for the root port, it's the port with the smallest path cost, which connect to the root bridge. The root port is responsible for forwarding data to the root bridge. The selection criteria for this port is based on the root path cost. So now we can know that for the root bridge, how we elect the root bridge. We compare the bridge ID, right? Because the root bridge has the smallest bridge ID, and then we just compare all the switches together with the bridge ID. Which one is the smaller? And then we choose this one as the root bridge. And for the root parts, actually this is this port it's determined by the root path cost. So the port connected to the root bridge, the cost, the smallest root path cost, it's with the smallest root path cost, it's the root part. So we compare the root path cost. And for the designed ports, the design port is for forwarding the configuration message to to the root port. Once the root bridge, the root port, and the design ports are successfully elected, the entry the entry tree topology is established. After the topology is stable, owning the root port and the design port forwarding the traffic, and the other non-root or non-design ports are in the blocking status. So the non-root and non-design ports are in the blocking status, and then the loops will be disappear, right? There are two basic matrices for the spanning tree generation calculation. The ID is divided into BID and PID, and the path cost. The BID is bridge ID. Bridge ID is composed of 16-bit bridge priority, and the bridge MAC address. Just now I said that we compare the bridge ID and then to elect the root bridge. And for the port ID, PID is composed of the two parts. The high 4 bits as a port priority, and the low 12 bits as a port number. So when the ports, when we compare the port ID, when the port priority are the same, and then we compare the port number, right? The smallest port number with the high priority. And for the path cost is a port variable, which is a reference value used by STP protocol to select a link. And the STP protocol calculates the path cost, selects a stronger link, and block X-case links, and prunes the network into a loop-free tree network structure. In an STP network, the path cost from a port to the root bridge is the path cost of each port on each bridge. So later, if we compare, if we want to elect the to calculate the path cost, we need to remember that the path cost from a port, the path cost is that a port is that the path from a port to the root bridge. This is the path cost of the port. And for the overhead, the calculation is based on the negotiate rate of a link 10 gigabit. 10 gigabit is 1, and 1 gigabit is 2. 100 Mbps is 19, and 10 Mbps is 100. Okay, for the STP elect rules, the minimum BID used to elect the root bridge. The minimum root path cost is used to select the root ports on a non-root bridge. And for the minimum sender BID, when a device running STP protocol selects the root ports among more than 2 ports with equal root path cost, as the STP will select the sender BID with a smaller standard BID from the received configuration message. And then it's the minimum PID, minimum port ID. used to block the port, which is the smallest PID. So here, uh, here there is a question for just now we have talked about how to elect the roads and the road port, the design port, and the blocking port. So here we give a question. For example, here we there is a top lodge, and the coast we already mark it here. The switch BID, bridge ID here. For this top lodge, which one is the bridge? Which one is the road bridge? It's a B, right? The answer is in the right side. So why we choose the B, the switch B as the road bridge? Because when we compare the bridge ID for the switch B, the bridge ID is 4096, and for the other the bridge ID, this one switch E, the bridge ID is 4096. The bridge ID is 36865. So this one and switch A, switch C, switch D, the bridge ID is bigger than B and E. So when the bridge ID of B and E is the same, and then we compare the MAC address, right? Because it's here, the BID is composed of the bridge priority. This is the bridge priority and the bridge MAC address. So here, when the bridge priority are the same 4096, and then we compare with the MAC address. The MAC address of switch B, it's this one, 12.2. So it's smaller. The MAC address is smaller than switch E. So we choose the switch B as the root bridge because it's the smallest bridge ID, and then the root switch B as the root. Okay, the next is we need to elect the root port. The root port. So the root port is with the smallest passcode to the root bridge, right? So in this top lodge, the smallest passcode to the root bridge, passcode for the switch E. This one is the root. For the switch C, the interface 3 connect to the root, and the cost is 2. And the cost is the smallest is 2. So the interface 3 of the switch C is the root port. And for the switch E, because each non-root bridge devices has one root port. So for the switch E, interface 1, it connected to the switch to the root bridge, and the cost is 1. So the interface 1 in switch E is a root port. And for switch A and switch D, because as you say, from the interface 2 to switch C, the cost 1, and from C to B, cost 2. So the total cost is 3. 3. And for the switch D, uh, this is from the A to B, the path cost 3. It's the smallest. Because if you want to go this way, from interface 1 to interface 2 and to C to B, it's not the smallest cost. So for the switch A, the interface 2, it's the root part. And for switch D, the interface 1 is the root port. So after we elect the root port, let's see what is the design port. Actually, for the design ports, for the design port, it's just in the non-root and non-root and non-design port as in the blocking state. For the design, the other ports are the design ports. In one switch, there is only one root port, and the others, this is the design ports. The next is the blocking ports. So why the blocking port is this two ports, the interface 2 in switch E and the interface 1 in switch A. Why these two ports we selected as the blocking ports? So at first we compare at first we select the root bridge is we compare the BID, right? We compare the priority and the MAC address. And when we choose the root port, we compare the path cost. And then for the blocking ports, for example, in the switch for the blocking port in the switch E, in the switch B, switch E connect to the switch B, and switch C connect also to the switch B. But when we compare, so for this link, for the link from switch C to switch E, we need to block it, right? Because if there is no blocking, if this link not blocking, there will be the loop between BCE. So there is not blocking port. But which port we choose as the blocking port? Okay, let's see. For the priority of switch C, the priority is 3 to it's this one. It's more bigger. And for the switch E, the priority is 4,000. So we compare with the priority, and then we choose switch E as we choose the ports which connect to the switch E as the blocking port. The same with the switch A. After we compare with this number, and we choose the interface 1 as the blocking port. This is for the STP electing rules. And for the STP ports status changing, uh, before the STP there has the four status: the forwarding status, the learning status. For the forwarding status, it's always forwarding the user's data and the BPDU message. And for the learning status, it will to learning the MAC address, but not forwarding the user data. And for the listening status, it will used for elect the road parts, road bridge, and the design parts. And for the blocking ports, uh, it receives the BPDU, but actually it doesn't handle this message, and also it not forward the user's data. And for the disable port, it not handle the BPDU packets, and also not transfer user data. Actually, for this disabled port, the status is shut down. So the STP protocol help to prevent the broadcast storm in the network, and also it prevents the MAC address table shocking. But is it the perfect protocol? Actually, no. Why? It's not perfect because uh, it's very slow. So in the STP, in the original STP, if if the topology of the network already change, and then uh, it will to the network will to generate the new spanning tree. So this step it takes a long time. The devices will need to wait a forwarding delay time. It's about the 30 seconds. So after the 30 seconds, uh, the new topology generated. So we'll change to the new topology. It's a long time, right? Because 30 seconds it's a long time. Uh, so to make the to improve to improve the topology changing time to make it shorter. So we the IEE the developed the second protocol. It's RSTP. The name of the RSTP is the Rapid Spanning Tree Protocol. Here we also shows that the shortcoming of STP are as below. The STP doesn't distinguish between port status and the port role in detail, so which is not conducive to learning the deployment for the beginners. And also the STP algorithm is a passive algorithm, so which depends on the timer waiting methods to judging the topology change, and the time for the waiting it's more than 30 seconds, and it's so long. And the third for the STP algorithm requires that in a stable topology, the road bridge actually send out the configuration BPDU, while the other devices proceed it as process it and spread it throughout the Intel STP network. So, according to the deficiency of STP, the RSTP based on 802.1W is proposed. And for RSTP, it deletes three port status. As we know, for the STP, it has the five status, but actually for the RSTP, it only three ports status. RSTP also adds corresponding some enhanced features and protection methods to achieve the network stability and rapid convergence. Now, before the STP, they have forwarding, learning, listening, blocking, and disable. The five port status, but for STP, it already changed to the three. It's the forwarding status, learning status, and discarding. For the discarding status, but for the discarding status, it includes the alternate port and the backup port. It also defines the two port role. Before it has the root port and the blocking port and the design port. But for RSTP, it has the alternate port and the backup port as the new role, add two new role in RSTP. There are four types of the RSTP port role: root port, design port, alternate port, and the backup port. For the root port and the design ports are the same as defining the STP. It's to forward the user data and to handle the BPDU packets. And for the new alternate port and the backup ports, from the perspective of configuring BPDU packet transmission, the alternate port is a port blocked due to learning configuration BPDU sent by other bridge. And for the backup port, it's the port that is blocked due to the learning configuration BPDU message sent by itself. From the perspective of the user traffic, the alternate port provides another switchable path from the design bridge to the root as a backup port or the root port. The backup port serves as a backup for the design port. So, it providing another backup path from the root bridge to the corresponding network segment. The processing of assigning roles to all ports in an RSTP domain is the process of entire network convergence. So all in words, for the alternate port, this is a backup of the root part. And for the backup port, this is the backup for the design port. The alternate port and the backup port, it's a backup of the root port and the design ports. For the config BPDU, after the topology is stable, the configured BPDU will be sent to the H switch from the root bridge. For the theory of the RSTP, I think we can leave it as as a homework for you to learn by yourself, and to save the time, we just passed it. So we just need to know that for the rapid STP, the advantage is that it can make the topology change time more a short time for changing the topology. So it will be more quickly. So the name is the rapid STP. It only need to wait for the three hellos time. After the three hellos time, it's about the 6 seconds, and then the topology will be changed. The next is the multiple STP. The RSTP has been improved on the basic of STP to achieve the rapid convergence of the network topology. But actually, there is another problem not been solved. It's that about the VLAN. Because for STP and for RSTP, all the VLAN just running in one STP. So sometimes some nodes, some switch nodes break down, but and the topology already changed, but the VLAN and then the VLAN cannot across to the switch, so it will cause the VLAN packets not available. Some VLAN cannot be forwarded. So how to solve the problem for the VLAN crossing the spanning tree? Therefore, the MSTP protocol based on 802.1s was introduced. To easily introduce this as MSTP, we can think about that for the multiple spanning tree, for the whole network, if we use the multiple spanning tree, we just divided the network into multiple different region, and each region, the name is we call it the multiple spanning tree region, and for each region, there are many for each region we for each region there is a multiple spanning tree in this region, and different instance contains with the different VLAN, and for each spanning tree it's called the multiple spanning tree instance. It's a multiple spanning tree instance. So for each instance, it has multiple VLAN already running on this instance. It's it's just like a group combined with the spanning tree. So by bundling the multiple VLANs into one instance, the communication overhead and resource occupancy can be saved. The calculation of the topology of each MSTP instance is independent of each other, and the load balance can be achieved on this instance. Actually, for now, usually we already use the MSTP because for nowadays the VLAN is really important and commonly used. So without MSTP, it will be hard for the VLAN. The last part is about spanning tree configuration. In the for the feed switch mode, feed switch mode in the switch management center, Ethernet management, there is we can find the STP settings, and in the spanning tree, we can add the STP policy. Here we can see the picture. From the settings, the general, we can choose what kind of spanning tree we use, the STP, RSTP, and MSTP. All the Sundray smart switch now support this spanning tree. So after we choose the spanning tree protocol, and then we can select the switch or unlock group just that enable the spanning tree. In the advanced configuration, you can choose to enable the spanning tree protocol, and then you can switch the port properties. The spanning tree mode defaults to the advanced mode, and the change the prevention loop mode in the upper right corner. So it can be changed to the simple mode. The spanning tree turned on by default is in the simple mode is MSTP, which uses a separate domain and has less configurable content. So after switching to the simple mode, change the anti-loop mode in the lower left corner to switch back to the advanced mode. For the spanning tree, there is another thing. It's about the loop detection. The loop detection is enabled on the interface and is used to detect whether the link below the interface is looped. The loop processing actions include the blocking ports, closing ports, and extending the loop VLANs. Use a loop detection message to determine whether there is a loop on each port. If the loop detection message is not received, we face the certain loop detection interval. It's considered that the loop on the port has been eliminated, and the port is automatically restored to the normal forwarding status. So after we configure the loop detection, the action upon when the loop be detected, the action will be block the ports. See from the picture, you can block the ports, and we choose the port group. Which port will be joined in this group. For the fight switch mode, it's how to enable the spanning tree. It's in the internet management, the STP configuration, and spanning tree. I can choose. Usually we use the MSTP, and we choose the MST region, and to add the VLAN to instance mapping. For the loop detection, we can add the loop detection just like the fit IP to input the name, to choose the action upon the loop detected, and to decide which port will join the loop detection policy. So detect the port, and if the loop detected, then the action will be block the port. Okay, this part is about the spanning tree. For the spanning tree, the theory it's not easy to understand, but configuration. the configuration in the fat AP or in the fit AP, it's not so hard to understand.